Well, we're really at quite a critical point where we're trying to get all the individual parts of EDSAC working together. And at the heart of that is the part of the machine called main control. Main control is the part that knows how to fetch the next order out of the memory of the machine, decode it, tell the arithmetic unit what it's supposed to do, and then when the arithmetic unit has finished its calculation, main control then has to know how to go on and fetch the next instruction. So for main control to do that, it's got to work with the clock system that tells it where in each word the data is and where the instruction code is and so forth. It has to talk to the coincidence system, which is the mechanism that makes main control wait until the data it needs is coming out of the delay lines in the store. And it has to talk to the arithmetic unit. So it's quite a complicated crossroads. And as you can imagine, there are a lot of signals that have to connect those various parts together. They have to be at compatible levels with each other in terms of the voltages and the shapes of the signals, and equally important in their timing. And so as we're trying to bring all these pieces together, we find there are differences, and we have to understand whether we go back to the originating system and make a change there, or whether main control has to be changed. And these are really difficult things to debug because everything is moving. The store is circulating, main control is trying to circulate through the program, the arithmetic unit is circulating through its calculations. And really these synchronization issues are critical. And there are some key timing signals that have to be absolutely right for everything to remain in synchronization.
It's January 2018. The regular team meeting concentrates today on a serious timing problem which has been holding up the integration of the machine.
The counter was not counting at all. And a very small tweak of the settings on the half adder caused it to burst into life.
We think at the moment the DC restore of the OR gates and things, which isn't present on the half adder input, the B inputs, we think that's drifting. We just need to put a scope on the grid and see what's happening there.
When I came to do it, it was indeed twitchy, and the reason it was twitchy is because there was a duff valve. But when we got it back, I think you can see that, you know, you could have quite a bit of a wiggle, and it was quite stable.
That works fine for the static situation, but for the counting situation, it's still very twitchy, which we just demonstrated. We've gone and turned it on, and it's not working at all now this morning.
Yeah.
We've been having quite a serious problem over the last 2 or 3 weeks, which is holding up progress, and it's to do with the counter circuit, which is up here on one of these racks here, which has to count up the digit pulses, the timing pulses which tell us where we are in a word, and this seems to be, on the one hand, fluctuating and not always counting correctly, and on the other hand, it's sometimes coming up with a trigger circuit out of phase with all the other bits in the counter tank. Technically, these parts are used for the display system on the one hand and controlling where words are in the tank on another hand.
Bits making up the instructions and data for EDSAC are circulating in the memory tanks all the time. It's crucial to know where the bits are so that they can be read off accurately and sent to other parts of the machine. That means counting them as they go round, with timings synchronized with the machine's clock. This is recorded by a counter which starts running as soon as the machine is switched on. To show the contents of memory on the operator's display screen, a special signal called trig 0 has to be generated when the first bit of the first number or instruction in memory is about to be recirculated. This signal starts the display scanning across the screen, showing the bits as they go by. The team have a problem because the trig 0 pulses have not been appearing reliably, and so they can't display the contents of the store. Is this the fault of the counter, the machine's clock and digit pulse system, or a problem in how the machine starts up?
What we found was that when the machine powered up, it's a bit indeterminate what state it comes up in, and it was possible for this counter unit to come up in one of two possible modes. One mode was correct and gave us this trigger which shows us where we are in memory, and the other mode came up incorrectly in an error state and would never show us where that point was.
Clearly there's an issue there, and we need more real information on what's happening.
So at our last meeting, in fact earlier this week, we had a discussion about the counter. This is an important part of the coincidence system. The counter tells you which word of the store is currently accessible.
A hardware correction module has been added to the loop. I only say apostrophe, it could be that these inherent faults or these inherent issues were there always.
It doesn't work without it either.
Yeah.
With the statics, a couple of times.
So it could be that this sensitivity, let's call it, has always been there.
It has worked in the past. With recent changes we've made, it has stopped working, and without it working, main control can't fetch instructions and data.
Surely what you should do is go back to the unmodified state and check that.
We have done that.
Yes.
Without
Right, okay.
success.
Without success.
Yes.
But well, you've got to go back to that state and start finding out what's wrong with that.
Well, that's what we did last week
Yeah.
with Nigel, but his setting up doesn't end up with counting, so there's a non sequitur somewhere in that.
The thing is that there's no good having little cliques of people working on single problems and trying to solve them, because the ramifications of what they're doing may influence everybody. And in particular may influence authenticity.
The general rule, the first thing to do is to get the counter counting. Is that correct, Chris?
I say the first thing to do is to revert to the circuit as it was in March.
Right. Is that
And then
10 minutes work, an hour's work?
That won't. That will have the trig naught problem, but that's a subsidiary
Let's
problem.
forget about that.
It still seems that the counter is not counting regularly, and that's a new situation which has not been there before. We're unsure about whether that's due to incorporating that trigger circuit modification, or it's intrinsic with the half adder and tank. And so what we've resolved to do is revert to the original circuit before we had to put the trigger circuit in, and concentrate on getting the counter to count regularly, and then after that, then we can introduce the triggers synchronizing circuit.
The counter clicks up from 1 to 32, but it's sensitive because there are many logical stages in the adder and the memory that can cause the signal to die down, and then it needs amplifying and cleaning up. And with valve technology, which is what we're working with, the signal levels have to be watched at every point and adjusted.
So we're using a modern piece of test equipment that we call the signal injector, that was designed and built by Tom Toth, another volunteer. And indeed that's been part of our general approach to make things easier for ourselves. We've built a lot of test equipment using modern transistor circuits, microprocessors and so forth that allow us to do rather more controlled tests than just powering the whole machine on and not quite knowing where the problems might be.
What I've been doing is helping James with the integration testing, the chassis testing on an individual basis and then testing them collectively, both statically and dynamically. By way of achieving that is we've built this signal sequence injector, which is designed initially to put digital data codes into the memory tanks, but the whole thing's expanded over the time to produce test pulses for testing various sub-assemblies as well, like bistables and monostables. It simulates order codes for testing subsystems, and no doubt it'll grow to include other functions as well over time. So, for example, this is a menu of sequences, and what I can do is I can select a sequence, say the first sequence, which is 576 bits in length. It's already hooked up to a tank, and it will toggle all the various signals that it needs to toggle, and I just press the insert button, which is this one on the end here. It transmits the signal into the tank, reads it back from the tank, compares the transmitted and read back signal, and validates or otherwise. So we've got good data in the tank. Then over to the other guys for commissioning.
I also found that tuning the pots in the half adder made a huge difference. So when we set it up statically, it seemed to be working, but as soon as we wanted counts, it was even more critical. And then we found a valve had failed, and so we're getting to the point where things are very sensitive depending on how the valves are working, and we're not sure where we're going from here, but at the moment it seems to be stable.
We're testing the counter which is used for the coincidence unit, which is part of the memory addressing system of the computer. The idea is that each of the long tanks contains 32 18-bit half words which are going around and around in circles all the time, and if we want to read one particular one of those half words from the memory, it's a question not of going somewhere in space to get the particular data, but you have to go to a particular place in time. Essentially, you have to wait for the correct one of the 32 words to come round in the circulation and then grab it as it goes past. Now, there's no direct way of knowing which word is which in the tanks. They don't identify themselves in any way. So what we have is a counter which is running in parallel with the tanks, and it takes the same length of time to count for the counter to roll over as it does for all of the words to go around the tank once. And to get a particular word out, we look at the value of the counter and compare it to the address of the word that we're interested in. And if those two are the same, we know it's the right word. If otherwise, we wait for the next one to go around and keep doing that. So we need this counter to count very stably so that it stays synchronized with the data that's going around in the tanks all the time. What we see here is a signal called trig 0, the pulse which is generated each time all 576 bits have gone once around the tank. At the bottom, is synchronized with that, is the contents of the counter. So you can see that the 5 bits that are always in the counter at the time that this top pulse happens are always 1, because the counter is at that point, the 5 bits of the counter are all 1s. And we've been having serious problems with making this counter stable, but we think after a month's work that we now have it running absolutely stably. And looking at Tom's box, which is also counting how often these trig 0 pulses happen, we can see that the ratio or the number of clocks between each of the trig 0 pulses is absolutely stable at 576. Before we had this running stably, we were having problems that bits were being dropped from the counter, and the time between each of the rollovers when the counter got to the maximum value wasn't stable at the correct value of 576. Before, we'd have always seen the top pulse, as long as it was being generated, would stay in the same place, because that's synchronized, the display on the scope is synchronized to that pulse. But the bottom pulses would have moved, especially these 5 pulses here. We wouldn't have necessarily seen those. This nice stable set of 5-1 pulses, which indicates that the counter is going to roll over.
We don't ever know what kind of snags we're going to come up against and how long they're going to take to fix. I mean, the recent problem with the counter is an example of coming up against an unexpected problem which nobody had guessed would happen. And came as a bit of a surprise.
The fix, which Chris Burton ingeniously came out with an ingenious fix, was to force D1 into the counter tank rather than it going through or in addition to it going through the half adder. And the addition of the OR gate and Chris Burton's neat little fix it's a synchronization fix essentially, so it keeps the counter tank in completely synchronized. So fingers crossed we can't go wrong.
We're in business, so that issue is now resolved.
So our approach in the construction of the replica is, as project manager, I asked various individuals to be the key designer for each subsystem, and then those people have a set of colleagues working with them who are helping them during the commissioning and the debugging. So, for example, the main control team who are here today are led by James Barr, and he's helped by Tom Toth, Tony Abbey and Simon Kelly, and they're primary interest is making main control talk to the rest of the system, but to do that they obviously have to interface to other parts. So for example, Nigel Benet is here today because he's done the design and indeed most of the construction of the arithmetic unit, and so he can confirm that they're sending the right signals and that he's sending the correct information back to them.
Okay, well this is the arithmetic logic unit and it's all ready to execute instructions. I'm waiting to get a signal down this little white wire here, labelled C26, which is order code 26, which will tell me to load the multiplier register. That'll be the first instruction, if you like, that I will execute on behalf of the computer. Meanwhile, we have to keep this thing exercised, and that's what this test equipment's doing. And it's just a means of just stimulating some of the circuits in the half adder to keep it ticking over, basically. So when the whole system is operating, the instructions decoded from memory will come over to the arithmetic logic unit. Briefly, these three racks here comprise the arithmetic logic unit and are fully functional. They've been tested with simulators. This system is now running on the system clock, so it's using all the important signals coming from the main parts of the machine are being used rather than the simulated ones that we had to manufacture back at Cambridge. So we're really happy that this is nice and stable. It's just waiting to receive some instructions to do something, and then it will do it.
Most of the memory access system was designed by a volunteer called John Pratt, who used to live locally. He's now moved away, and so some of the team members here, Simon in particular, have taken on responsibility for looking after that bit of the system as well. And at this time, getting main control and the store access and coincidence system working together is the key area of focus. So it makes sense for the main control team to take on that responsibility also. We have other people. Peter Lawrence and John Sanderson built the clock system. That fortunately is working well and seems to behave itself, so they're not here today. And then we have the input-output system. That's still being built, led by a man called Martin Evans and a colleague, David Milway, who are building the parts in Cambridge. The other major part of the system are the delay lines in the store. They're being built in a team led by Peter Linnington. And of course, there's the power supply, which was built by Alex Passmore. So those people come if they're needed to solve problems with their particular parts. As I've said, at the moment, we're mostly concerned with main control, and main control is dependent on the clock, on the store, and on the arithmetic unit. So those are the most busy people. And then the initial orders unit is being worked on by Peter Lawrence and John Sanderson. They developed the clock system early on. That's working quite reliably, and so it made sense for them to transfer their interest to initial instructions. They've built the Selector unit. There are 2 racks of electronics associated with it, and those are in the process of being designed.
Now we've moved on to this circuit, which I'm just looking at the moment, which is the panel 46 order tank control, where we're trying to get a coincidence pulse when one count matches another. And the first count is working, but I'm on to the next counter, which now isn't working, and I'm trying to find out whether the connections have fallen off or whether the circuit itself doesn't work.
Our next step is to inject an example test program, an application program, directly into one of the tanks. And the tank we've chosen is tank 0, tank 1, the lowest point in memory. We've chosen that one because we can restrict the machine to operate just on one tank, whereas the full-size machine, of course, in the end had 16. We're just going to use one, and we can write a quite decent test program in 32 instructions, which will prove that the master control unit is cycling through the fetch, execute sequence for every instruction correctly.
The pioneers would have worked using just voltmeters and ammeters and the oscilloscopes of the period that weren't as good as modern ones. But then they were working 5 days a week, 8 hours a day on the project. They were paid employees, and they're obviously much more familiar with the technology because it was of their period. So I think for ourselves, where we have less time because we're dependent on volunteer effort, and not all of us grew up in the valve era, using modern aids to help us is a practical thing to do. The important thing is what we will leave behind, so to speak, once we've got the machine working, is a machine all of whose circuits work as they did in the original EDSAC.